Okay, so this PowerPoint will look at energy changes uh, by using the direct method in a chemical reaction, how to calculate energy change. The three different reactions that students quite struggle with, or types of reactions that they struggle with, and using the E equals mcT delta T equation for each one, they find it very hard to find out what M is and delta T, which I'm going to go through. So obviously we're going to use D equals mcT. We're going to make sure that you don't make a mistake by missing out moles. And when we calculate energy, we must convert this energy to a delta H, which is per mole. So that's another mistake which I'll go through as well. And then making any silly mistakes in terms of conversion of units we'll look at as well. And then I'll give you a slide with possible errors that can occur. So the three different reactions is burning fuels, as you can see on the left, which requires a thermometer, heat shields to make sure the heat is not radiated away from the beaker and is going towards the beaker, although some will always be lost. And in the beaker we add roughly 100 centimeter cube, or measured amount of 100 centimeter cubed of water, but that is important that you know how much water you add. So if you add 90, you must record it as 90. And then obviously you have a spirit burner to burn the fuel, which is what we're looking at. We're trying to work out the energy that there is in a certain amount of fuel. And we're going to use it equals mcT. So the first thing, what is M? M is the mass of the water in the beaker. So if it's 100 centimeter cubed, it should be 100 grams, assuming that the density of water we take as 1 gram per centimeter cubed. So M is always the amount of water that we have in the beaker. And specific capacity, which is how much heat is absorbed by the water, effectively, is always taken as 4.18 as a constant, which will be given to you in an exam. And the temperature change is your starting temperature of the water before the flame is started to burn, and then you sort of measure temperature rise, and then you sort of switch it off, turn it off the flame and put a lid on it, and that's your final temperature the water reaches. So temperature change, although temperature should be in Kelvin, we can use here degrees centigrade. So that's the first thing we have to look at here, these three factors, that you know what M is and what everything is. So M is not the mass of the fuel burnt in this reaction. That's a common mistake that students make. So M is not the mass of fuel burnt. Be very careful there. The other two types of reactions is a solid reacting with solution. So for example, magnesium metal reacting with a certain volume of acid, or two solutions which are reacting in, for example, neutralization reaction. So again, applying the equals mcT to the second example, which is B, M will be the mass of sulfuric acid or hydrochloric acid or whatever acid or solution you are using in the beaker. So in this case it's 100. Although I put 50 there, you can ignore the 50 there, that's just a mistake. So we got 100 there, so that's why I used 100 there. And obviously the constant 4.18 will be the same. So whether you use an acid, whether you use water, this constant never changes unless they give you the density of the water, which we can look at later on in next PowerPoints. And the temperature change I already mentioned. Make sure you use the if rule, which I'll explain when I go through it with an example. In the next example, we're going to have two solutions, 50 centimeter cubed of alkali, 50 centimeter cubed of hydrochloric acid. So therefore, we're going to first add one of the chemicals, let's say sodium hydroxide, and measure the initial temperature. And then we're going to add 50 centimeter cubed for the reaction to start, and it will reach 100 centimeter cubed. So we want the final mass of the reaction, not the initial 50, the final. So we always add the two volumes together. Note we did not add the mass of the magnesium here to the thing. We don't need to do that unless they give you the mass of the whole reaction mixture, which we can look at later on in next PowerPoints. So this is the total volume of the two chemicals that are reacting. Again, specific heat capacity C is a constant like pi. That doesn't change, doesn't matter what solution we're using in chemistry. And always the temperature change is the initial temperature of the 50 centimeter cubed of the alkali, and 50 centimeter cubed of the acid mixed with the alkali is the total mass, which is 100. So do not use measure the final temperature when they're both added, because we need the initial temperature before the reaction as well. I haven't added lids to any of the beakers at all, just to save me time preparing the PowerPoint. But any heat experiments, lids should be on the top, and there should be some lagging on the beak around the beakers for these two. Obviously, you can't put lagging on the first one because you're going to apply a flame. You don't want the lagging to catch fire. So let's look at the first one, burning the fuel. So I put a brief method there, which you can read in your own time. But there's the initial temperature of the solution. Okay, there's the initial temperature of the spirit burner. So without we burning the chemical at all yet. And then once we burn a certain amount of fuel, it reaches, let's say, 40 degrees. Then we switch it off and we measure the final mass of the spirit burner, which in this case was 9.5. But we have to do that quickly because obviously fuel will evaporate and that will cause some errors in the experiment. We must put a lid over the spirit burner here so there's no evaporation of the fuel once we stop, and we quickly measure the mass so we've got the true mass of the fuel that we burnt. So using the E equals mcT, that's a constant 4.2 or 4.18, which will be given to an exam. First we calculate delta E. So mass is 100 because I told you that's the volume of in the water in the beaker. Times it by 4.2. There's your if rule, or should I say initial temperature minus the final temperature, which should give you a negative answer, which I didn't put here, but you can put the negative answer when you calculate the energy. So the first step is to calculate the energy, and if there's a negative value there, you can still add it there. There's nothing wrong in saying that. That just means energy has been lost in this reaction. Moles of fuel, well, we know the initial mass is 10. We know the final mass is 9.5. If you take the difference, you will see is 0.5. Divide by the MR that was given, or you have to calculate it, and that'll give you the moles of the fuel burnt. So make sure you use 3 sig fig minimum, otherwise there will be massive errors in your final answer. And the final step is to calculate delta H for this reaction. And delta H is basically your delta E divided by moles, which is minus 577 kilojoules per mole. In other words, when this fuel burnt, it released 577 kilojoules per mole. And we always divide by moles because that allows us to compare per mole. Otherwise, we can't compare different energies for different fuels. And this is worth 5 marks. Delta E, obviously, using the equation. Moles, obviously, using the equation that you've been taught, mass over MR. And difference between delta E and delta H is that it will be just divided by moles. A crucial step that a lot of people miss out. And a lot of people miss out the sign, which is why if you use the if rule, the sign comes in the first place straight away, so you don't forget to transpose it back into the final answer. If you give a positive answer there, you'll still get a mark there, but a positive answer here will lose you the mark. So it's crucial that you don't forget the sign. So simple 4 or 5 marks you can lose. The 5th mark is obviously for 3 sig fig as your final answer. And that's what I meant by if rule. If you do initial minus final always in terms of temperature change, you will see if it's negative, it's exothermic. If it's positive, it's endothermic. If you look at the second example, you can read this in your own time. So we're mixing calcium carbonate solid with, let's say, for example, 100 centimeter cubed of HCl of certain concentration. So again, there's your E equals mcT. There's your equation. Okay, the equation is very important because here you'll see it's 1 mole reacting with 2 moles So once you do step 1, calculate energy, which I've already showed you previously, and always convert it to kilojoules so you don't forget it at the end. I always convert it to kilojoules. You don't need to. You will get marks either for 1680 or 1.680. But if you convert it now, then you don't make a mistake at the end. Common mistakes in an exam. Second step is to work out the moles of both calcium carbonate and the HCl concentration times volume mass over mR, and you try to identify the limiting reagent, which I'll go into more detail in a separate PowerPoint. So we see here that limiting reagent is calcium carbonate, i.e. we've got less calcium carbonate there. We've got excess HCl, so always use the limiting reagent, in this case 7.99 times 10 to the minus 3 moles of calcium carbonate. Well, that will affect the amount of energy that's produced in the reaction, and that is used in step 3. So step 3, the 1.68 is divided by 7.99 times 10 to the minus 3, which gives you an overall energy change of positive 210 kilojoules per mole, which is an endothermic reaction. So make sure you don't use HCl, which is this here, in your final step. Otherwise, that's a massive error. Again, this could be worth up to 7 marks because the extra marks is in step 2 to calculate the moles of both and show which one is a limiting reagent. As an examiner, I found out in AQA, a lot of people made the step 2 as a mistake. They couldn't identify the limiting reagent. Let's look at the two solutions method. Again, I'm giving you the method there, a brief method there. So there's two solutions, 50 centimeter cube each, and let's assume it's 2 mole per decimeter cubed of each concentration. You got the initial temperature there, you got the final temperature there of the acids as well. So you always need the equation that gives you a mark usually. C is obviously given to you, and you need the equation, and you see here the equation here is 1 to 1. Oh, I made a mistake there, that's supposed to be 1. So can you just make sure you change that to 1? It's not 2 there. Once you do it 1 to 1, you have to calculate the E value first, which is standard for every single one of them, and change it to kilojoules, which is plus 5.67. Get the moles of both, and you'll see it's the same. And because it's 1 to 1, again, ignore the 2 here. That 2 shouldn't be there. It's wrong balancing. There is no excess there, so it does not matter which moles we use because they're both the same. So when you do step 3, you use the energy from step 1, you use the moles from step 2 to get the final energy change for the reaction, which is negative exothermic 56.7 kilojoules per mole. Common mistakes, like I already told you, forgetting the sign. So if you use the if rule, that avoids that. Common mistake is you forget to convert to kilojoules, so try to use that conversion or do the conversion in the first step always. Make sure you always read the question again, reread it again to see how many decimal places or significant figures you want your final answer to be. All part answers should be to 3 sig fig and more. And make sure when you calculate delta E, you must divide by moles to get it to delta H. That's the only difference between delta E and delta H. One is per mole and one is the energy value. So that's only for comparison purposes. If there's any limiting reagent, ignore any excess reagent. Again, that's another common mistake. And if in doubt, it's best to apply one of the moles and get at least 4 marks than getting no marks. So at least choose one of the moles if you are in doubt in an exam. But please learn how to calculate limiting reagents. And obviously converting the units I already told you. You don't need to convert the temperature in degrees centigrade because anytime you have a change, that conversion factor cancels out. So experimental value versus actual value. This is a very high level question. They always ask you for 1 or 2 marks. Obviously, we can look at that in next PowerPoints. But common mistakes are we don't stir the solution. So when you have a temperature in a solution, it's best to stir the solution so the heat is spread evenly, so we get a fair temperature reading for the initial and for the final. Lid, lagging, and heat shields to avoid heat loss to the surrounding. So the answer we get for number two is usually a lower answer because we do get heat loss even after doing all this. But if you don't stir, it can lead to a higher value or a lower value depending on where your thermometer is. If it's closer to the bottom, you'll get a higher value. If it's to the top where there's less heat spread, maybe, you can get a lower value. Using larger volume in an experiment obviously can lead to an error because a larger volume, the heat is spread more evenly, and therefore you'll get a lower temperature change, which means a lower heat energy change. So therefore, we must make sure we measure the volume as precisely as possible, i.e. use, for example, a burette or a pipette, not a measuring cylinder. When we're looking at solid, if we measure the solid also, if you use one decimal place, it's a lot, whereas using a balance which has got more decimal places is more precise, more accurate in terms of their mass. So therefore you get a better answer in your delta H value at the end. So you can discuss these factors with your teacher and that will help you answer the more harder level questions, which is probably B and A grade questions. Thank you for watching my PowerPoint for this one. I hope it helped you some to a certain extent. The next PowerPoint that I'm working on is calculated energy indirectly using Hess's law. Thank you very much.